I got distracted. Anyway, so okay, so what did I say? So when a conservative force field takes over, what happens? The charges will lose potential energy, right? They will go from higher. They have higher potential energy. Higher potential energy is going to turn into kinetic energy, so they start losing potential energy, right? In this direction. So the potential energy per charge is known as voltage, right? So the charges will go from regions of high voltage towards the low voltage. That's what it means. So what does that mean to you at this point? It means nothing. It's like blah 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 blah, and that's perfectly okay, just for now. But the next time around we come back to this topic, this is going to be a lot clearer, provided that you don't drink too much over the weekend. All right, so you got the high voltage potential, and the charges will go from high voltage towards the low voltage. That's what I'm talking about. Okay, so what does it mean to you? Nothing is yet, but it's going to mean something. All right, this little example that I gave you, which was actually fun. I love this commercial. All right, let's turn this into a simple problem. All right, I got disconnected. Okay, do you remember? I ended up putting a lot of emphasis on this one. There's a good reason for it, because conceptually this is going to play an important role in terms of understanding lighting. Also, the difference between how the TVs used to work versus how they work today. All right, what do we know? All right, so you got a capacitor. One region is positive charge, the other region is negative charge. You guys understand that the strength of the electric field here is going to be constant, right? Okay, I mean, we have done two derivations of that. All right, so the strength of the electric field is going to be constant within this region because the charge density is going to be constant. The reason surface charge density is going to be constant, Q divided by A is the surface charge density, because the charges will be uniformly distributed on a flat surface just like that. Okay, so what would happen if we were to drop a charge into that region? Notice that there's electric field and there's separation distance, so which means that the energy is already stored within this region. That's your potential or potential difference. As soon as you drop a charge in it, the charge becomes energized, meaning that this charge now has potential energy. And now when you let the charge go, potential energy turns into kinetic energy. All right, so voltage or potential is the amount of energy stored within this region, and when you drop a charge in it, now the charge has potential. All right, problem number 2. Okay, let's try to do problem number 2. Okay. It says 5,000 volts, and this problem is not the same as that problem. Okay, this is related to a TV tube, cathode ray TV tube. That's the way the technology was up until 15 years ago, I think. All right, so the electrons are going to be accelerated within this region for a voltage difference of 25,000 volts. And so the electrons will start from rest. Okay, so there's usually like filament, you heat it up so the electrons become ionized. Find the electron speed just before the electrons strike the screen. So what we're looking for is the speed with which they will actually leave this hole. All right, so let's set that up. What we're setting. Okay, so let's do this. So what do I know? I know that the voltage potential difference is 25,000 volts, and our charge is an electron. So it's a unit charge that we got. So what else do we have? We got the speed of this electron. All right, so let me change the notations a little bit. This is the speed in terms of meters per second, and maybe expecting in terms of light speed. I'm just curious what that speed is going to be. All right. The second thing I'm going to do is look at some visual. I usually come up with a way to visualize it, so you can see the details better. So one region is going to be negative charge. So this is the capacitor. This is negative charge, so the electrons will be liberated somehow. You got a filament. And the other region is going to be positive charge. And we are interested in the speed of this electron as it's leaving this region. So that's what we're interested in. What's given to us is the potential or voltage difference within this region. Right? Potential or voltage difference. Okay, so the couple of things that we know about this. So this is the speed. Initial speed. So what does it say? Initial speed is going to be 0. Here. So that's what we got. Alright, so how do you do a problem? There are a couple of ways you can do this problem, but one way, easiest way of doing it is the following. If you understand everything that we've been discussing so far, you know this force is an electrostatic force field, right? So that's, you got the electric field. The electrostatic force field is a conservative force field. So what happens is there's voltage or potential, which is there's energy stored within this region. When you drop a charge in. So what is the charge having? It's got potential energy, right? So what happens to the potential energy of this charge? The electric field acting on this charge is going to apply a force on it, and that's a conservative force field, which is QE. So which means that the charge is going to accelerate in this direction. Right? What kind of acceleration is that? It's a constant acceleration because the force is constant. That's actually a predictable motion. So you can actually use the kinematics equations if you wanted to, but I want to do something fun. All right, so here's an electrostatic force field. This is a conservative force field. Now the charge is going to have potential energy. So what happens to that potential energy at this point is going to turn into kinetic energy. All right, that's it. There are two ways of doing it. You can use kinetic equations or you can use the conservation of energy. For me, the lazy way of doing it is, hey, I already know what this is. I don't have a value for the electric field, but I know the amount of energy stored within this region. So if I drop a charge in it, now you get the potential energy. So what happens to that potential energy? The potential energy is going to go down. The kinetic energy is going to go up. All right, so that's the fourth energy. All right, now that I talked about it, okay, so conservative force field is going to do work. It's going to reduce the potential energy of the system as it's increasing the kinetic energy of these things. All right, so potential energy is going to go down. And the change of potential energy is the same as change of potential when you drop a charge in it. All right, so this is the charge that we got. All right, change in potential energy, this is V, not U, this is V. All right, change in potential energy. Potential difference times Q, potential times Q is the amount of energy stored within that region. All right, so positive or negative doesn't mean anything in terms of potential difference. So this term that you're looking at, this negative doesn't mean anything. It's there in terms of blah, blah, blah. Conservative force, you're going to reduce the potential energy, increase the kinetic energy. In terms of electrostatic, understand that it's there. And you will know shortly that you can just ignore that sign for the most part and get away with it. And there's a reason for it. When I first start to talk about the height analogy or the potential difference, the meaning of it. Because potential difference is always expressed in terms of sometimes an arbitrary reference point. Okay, so having said that, I usually, okay, so substitute back and ignore the sign for whatever reason. All right, so this is going to be Q, delta V, which means that the kinetic energy is going to change. All right, so that represents the change in kinetic energy. And change of potential energy is the same as potential. That's what I was getting at. That's how you can get away with getting rid of the sign. So then you're going to get rid of that. And what do you have? Okay, so Q is the same as E. Q is the same as E, which means that, hey, I love this stuff. I mean, you can just erase it. So cool. And the initial speed is 0, so this initial speed is going to drop out, so that thing goes away. Alright, so all of a sudden we got it. It's going to be 1/2 mv squared E. Okay, let's not confuse these. Alright, so that's what it. Delta V. And then boom. Oh, this is good. Alright, and then plug the numbers in, whatever the numbers are. Alright, the only thing you will really, when you go back and review this, okay, how you get rid of this negative is the one you will have a hard time understanding. Okay, so which means that you will have to come back and revisit it. Okay, because you guys are a little bit used to rigorous math, and we do a little bit of hand-waving arguments at this point. That's what I did. And some of you guys will have a tendency to get rid of it by knowing that this charge is negative. Okay, in reality, whatever voltage or potential means, it depends on how you reference 2 points. Potential voltage depends on which one is a negative, which one is a positive, which one is a negative voltage, which one is a positive. All right, you can take this to be 0 and you can take this to be positive. Or you can take this to be 0, you can take this to be negative. Okay, so it depends on how you reference it. It's very arbitrary in terms of. So that's the reason why we always talk about the potential difference. If you're talking about the potential difference in reality, you don't have to worry about numbers, whatever that means. It's not a big deal right now, but we need to come back and we need to clarify that one more time at some point. Okay, so this was a nice, easy exercise. So let's move on to something electric field. All right, so the voltage represents the amount of energy stored within the electric field per charge. So we do explanation. All right, problem number 4 is an extension of problem number 2. All right, so once again, the voltage difference is going to be 25,000 volts. Okay, so the plate distance, separation distance is going to be 1.5 centimeters. Find the magnitude of the uniform electric field within that region. Okay, so which means that I can follow through with this concept. Because I also want to be able to use the kinematics equation. All right. So this is problem number 4. Number Okay. All right, problem number 4. So it's related to the same problem as before. So what do we have this time? Okay, so 25,000 volts, separation distance is 1.5 centimeters. Figure out the magnitude of the electric field within that region. And that's it. So that's what we know. We'll do once again, yes. Voltage potential difference is the same as voltage. So it's going to be 25,000 volts. And the standard separation distance is 1.5 centimeters, which is the same as 0.015 meters. And then figure out the strength of the electric field in between in terms of meters per coulomb. And that's pretty much it. Nothing similar, just pick this up. Okay, so we're done with the same region, the same setup. Alright, so R in this case is the separation distance. And that's it. What else do we have? That's all we have. Okay. Okay, just I'm gonna do a little bit more than this. Okay, so in terms of the math, voltage or potential difference is the same as this is the amount of energy stored within the strength of the electric field between the separation distance. We can draw opposite side regions, so that's it. So solve for E, and then we're done. Alright, so I'm gonna plug the numbers in. And then whatever that number is, more than likely, I don't know what that number is. Okay, I'm curious if this is the number we got. Alright, okay, so do yourself a number. Also, did you get this number by any chance?
Yes.
Okay.
Yeah, I guess I did 4.
So these numbers are correct, right? Okay, give yourself some points if you're doing the number. Okay, guys, just out of curiosity, just for the hell of it, okay? Because there are various ways you can solve this problem. Okay. So what I want to do is now that we got this number, okay, what is this? This is the strength of the electric. Okay, so let's go back and let's redo problem number 2 by using the kinematics equation. Okay, I'm just curious if you get the same answer.